same. And now today we are going to start with some more properties as such, but let us just write a few things. So just a revision of what we have done. Just a revision of what we've done. So till now we have done that your f of x, if it is a periodic function, then I can represent, if f of x is a periodic function, then I can represent this periodic function in terms of, in you can say, in a discrete basis of orthonormal function. And these orthonormal functions are nothing but they are sines and cosines. They are sines and cosines. So what I can do, if my f of x is a periodic function, then this particular periodic function can be written in the discrete basis of orthonormal functions, that is sine and the cosine. But when we have to write a representation for an aperiodic function, what I can do, or in fact for any other function, but if the basis is discrete, instead of discrete basis, we have a continuous basis, then this particular Fourier series, here you have this Fourier series. When we say that my function f of x is a periodic function and I'm writing it in the discrete basis set of orthonormal functions like sines and cosine, then this forms the Fourier series. And if instead of discrete basis we take continuous basis, then this is nothing but this is actually equal to the Fourier transform of the function f of x. Or in other words, I can say that my Fourier transform is defined as minus infinite to plus infinite f of x e की power minus iota kx. And just don't worry about all these things. In exam, if the question will come, it will actually give you this the way they are defining. So at times you'll find that 1 upon root 2 pi is not written, at times you'll find 1 upon root 2 pi is written. So it depends how the examiner sets your question, but overall understand the point that this is the Fourier transform, and the inverse Fourier transform will then it be, and understand, you say this also Fourier transform, you say this also Fourier transform, so both are Fourier transforms of each other. So this will be like 1 upon minus infinity to plus infinity, this will be f tilde k, and I can write e की power iota kx dk. Okay, so this is one thing. Now let us start with another let us start with today's discussion. And okay, so basically what is the help of what do we intend to get from transform in general? Always remember, transform is done in order to simplify your problem. So for example, here you were solving a problem in x space, and probably solving a problem in k space is a little bit easier. So what I'll do, I'll go via x space to k space, whether through, you can take as Fourier transform, in Laplace transform you by transform in general, and by inverse transform you can again get back the solution. So this is one of the important thing that one can do. So basically what you're doing, you're moving from a coordinate space to a k space. Okay, you are moving from coordinate space to the k space. But when you are doing a Fourier transform, okay. So for example, just to remind you, for example, in quantum mechanics, for example, we have studied the Schrodinger equation. And solved it for some simple systems like you can take them as your hydrogen atom, simple systems like hydrogen atom, or relatively easier one will be to say simple harmonic oscillator, or you can say particle in a box. So in quantum mechanics, Schrodinger equation for some simple systems are usually written in terms of wave function. You see the solutions are solutions of these Schrodinger equations are nothing but these psi of x. So basically you're writing a wave function and this x is there. So I'll say that I'm writing the wave function in terms of the coordinate space. This is called as coordinate space because I'm writing in terms of x. Okay. Or I can write psi of r if it is a three-dimensional problem. Okay, so in general I can say that these wave functions depend upon the position. Positions, and I'll say that these wave functions are a part of configuration space. This is at times referred to as configuration space or coordinate space, you can say. Okay, and now understand, for a particular quantum mechanical system it is more preferred to work in momentum space. For a particular quantum systems, you can say, for particular quantum systems, uh, it is more convenient. It is more convenient to solve, you can say, Schrodinger equation, or to find the wave function, in uh, an equivalent space, called as momentum space. So again, so you have to transform your wave function from one coordinate space or configuration space into the momentum space. Now, this particular conversion is related by we'll see all these things later on in quantum mechanics, but this right now, because we are discussing Fourier transform, so this particular transformation is related by Fourier transform. So your psi of x, you can write it as 1 upon root 2 pi h cat minus infinite to plus infinite. You have this phi of p, which is the wave function in the momentum space, in terms of momenta, e की power iota p x upon h cat, and then this is dp. And similarly, if you want to write this phi p, this phi p is nothing but it is equals to 1 upon root over 2 pi h cat from minus infinite to plus infinite, and this is psi of x, and then you will write e की power minus iota p x upon h cat, and then you have this d of x. So both, like, this is how you can relate, that is the wave function in the coordinate space can be is nothing but it is equal to the Fourier transform of the wave function in the momentum space. What is wave function in the momentum space? It is the Fourier transform of the wave function in the coordinate space. Okay, so basically what happens is, for example, you have momentum profile. So whenever you are going to study, let's say, scattering problems, okay, so what should I write? Let's say, for example, when you are studying the scattering problems, so at times in scattering problems, when it comes to research or somewhere, you'll find that momentum profiles are given to you. Okay, or for example, let's say, for example, Compton scattering. For example, Compton is scattering from atomic electrons. Okay, here you know that the data that we derive from experimental condition is the wavelength distribution. We get the wavelength distribution. We get the wavelength distribution of scattered radiation of the scattered radiation, and which eventually depends upon the momentum distribution, which eventually depends on the momentum distribution of momentum distribution of the target electrons. So I want to suggest is that in these kind of problem, for example in scattering problem, the data that you get from the experiment, or more generally, it is very easier to identify things in terms of momentum space. So basically there it is required that the wave function should be expressed in the momentum space. The wave function must be expressed in terms of the momentum space. Okay. Okay, so this is one thing. Now, another application that is quite important as far as physics is concerned is to see that there is something called as Dirac delta function that we did in quite many lectures that are in the right now in the folder called as quantum mechanics, or in mathematical physics you can say. I have done that for you. Now, one of the important representations, you know that Dirac delta functions can be Dirac delta function can be represented in various ways, in various ways. Like for example, when we did Dirac delta function, we saw that it can be represented in terms of limit of sequences of some function. Now, one of the most you can say that utilized sort of representation is the integral representation, and this is quite important for you. Just remember this: integral representation of Dirac delta function. Integral representation of Dirac delta function. So you know that this particular Dirac delta function can be represented in terms of limit of sequences of some function, which we have discussed. For example, rectangular functions, sets of Lorentzians, sets of Gaussians, family of Gaussians, and all those sort of things. Now, here we are discussing something called as the integral representation of the Dirac delta function, and I would write it straight way that the integral representation is this. That is, if I want to write my Dirac delta function, that is Dirac of x minus of x naught, I can write it as 1 upon 2 pi, and from minus infinite to plus infinite, I can write e की power iota k x minus x naught, and I will write simply dk. So remember, if here you have this x minus x naught, I have written dk here. So basically when I integrate this argument which is attached to this variable, that is the variable iota k, whatever argument is attached, it goes into the argument, it goes as an argument of Dirac delta function. I hope it is clear till now. So this is the definition, so don't worry about it. Is that clear, or should I repeat it? Kindly let me know in the comment section if anybody is watching it right now. So let me just generate a small proof for it, so that you will be able to relate more. So what is the proof for it? So for example, I know what is Dirac delta function. So one thing that is quite sure, that I know what is Dirac delta function. So for example, if I say that my Dirac delta function is stationed at x equal to 0. So for example, if I have this Dirac delta function which is stationed, that is if it is situated at x equal to 0, then I will write it as infinity if x is equal to 0, x equal to 0, and if x is not equal to 0, then I will write it as 0. And further, I know that if I want to integrate it from minus infinity to plus infinity Dirac delta function, then this particular thing would give me unity, that is 1. Now one has to understand there's something called as filtering property, and if you're not aware, kindly see my lectures on Dirac delta function. There's something called as filtering property. So let's say if I am integrating fy and there is a Dirac function Dirac of x minus y dy, then this is nothing but this is equals to f of x. So basically what happens, and just don't get confused, Dirac delta function is a symmetric function. So whether you write Dirac of x minus y or whether you write Dirac of y minus it is one and the same thing. So what happens, whatever argument is written here, so for example I write it as Dirac of y minus of x. So basically Dirac delta function is situated at x. So at x you'll find a very high narrow peak. So basically when I'm writing Dirac delta function Dirac of x, which is situated at x equal to 0, it implies that I have a very narrow peak at x equal to 0, and whenever x is not equal to 0, this is simply 0, and this particular peaks the area is given to be unity. That is the area under this narrow peak is simply unity, that is 1. Okay, so using this filtering property, see, one has to also understand this is one, this is called as filtering property. That is, for example, if it's confusing you x and y, so I'll write it here. For example, if you have f of x and you are writing Dirac of x minus x naught, so where Dirac is situated at x equal to x naught, then this particular integration is nothing but it is equal to f of x naught. Okay, this particular integral is something like f of x naught. Basically what is happening, wherever Dirac is situated, that particular point where Dirac is situated, it gets into the argument of the function, and this is an answer, that is f of x naught. This is called as the filtering property for the Dirac delta function. Now you see, when I was defining the pair of, so when we define pair of Fourier transform, what was happening? So for example, if I want to write in terms of x and y only, so what I'll do, I'll simply write fx, and instead of writing k, I will use y now. So this is root over 1 minus infinity to infinity. This I used to write gk, now I'm writing gy e to the power iota x y and then dy. So basically what is this? Gy is the Fourier transform of f of x, and this is the inverse Fourier transform. So basically and how this gy is like, you can take anything like gy, you can write as Fourier transform, then this will be in Fourier transform. So always remember, this may give you certain difficulties in exam. So basically in exam what will happen, in exam you don't have to remember the formula, probably they will give you the formula. Basically what they want you is that, for example, here I'm finding the inverse Fourier transform, so I have not kept a negative here. So but understand both of them are Fourier transforms only. So this kind of confusion usually exists in the examination, so it's better to see what your examiner has given to you. So for example, they will give you the definition. So otherwise I'm writing it for you, 1 upon root 2 pi, 1 upon root 2 pi. Here you will have f of x, here you will have iota x, and then you will have minus here, and then you will write dx here. Okay, so these are the pair of Fourier transforms. So these are the pair of the Fourier transform. Now you see, f of x, if I want to write f of x, I can also write f of x as simply integral from minus infinity to plus infinity f of y Dirac of x minus y dy. This is one. And also remember, let's say this is your equation number 1, and let us say this is your equation number 2. So basically what is happening, this is, let's say, your equation number 1, and this is, let's say, equation number 2. So what I can use instead of gy this also, but the problem that will come is that here these variables are same. What will happen when you will take this particular gy inside then one has to use a different variable, because otherwise it will get muddled up. So one has to remember, whenever you are taking, let's say, double sums. So for example, if you are taking double sums also, what happens is, if you are taking index here n, then I take index m here, so that it does not create confusion. The similar thing exists in integrals also. So for example, if I have to write what is f of x, so I'll try to use the different variable. So with f of x, for this I'll use the different variable. So use different variable. Okay. So what will happen? This will come out as 1 upon 2 pi, because see, 1 upon root 2 pi, 1 upon root 2 pi, this will become 1 upon pi, and this is minus infinite to plus infinite. Instead of g of y, I'm writing what? I'm again writing minus infinite to plus infinite. I'm writing f of x dash e to the power minus iota x dash y dx dash. There is also e to the power iota xy, so I will write it here. I will write dy here. After integrating this, you have to take the e to the power iota xy. Okay. So this is how you're going to write things up. Now what will happen? Now if you write what is f of x. So now if I write what is f of x is 1 upon 2 pi minus infinite to plus infinite. If I take this dx dash and like dx dash and fx dash outside, so basically what I'll do, I'll take dx dash and fx dash outside, and this integration from minus infinite to plus infinite, I will write fx dash, or not fx dash, sorry, I will simply write e to the power iota, what is remaining, x minus x dash y, and then dy. Now just think about it. So for example, this fx dash I have taken with dx dash, and remaining these terms, because here you have variable y, here you have variable y, so I have integrated with respect to dy. Okay, now compare it with the first equation, that is the equation we had in terms of the Dirac delta function. So f of x can also be written as integration from minus infinite to plus infinite f of y Dirac of x minus instead of y, I will write instead of okay, so I know this is I'll write it once एक बार इसको लिखते हैं dy. Okay, now if I compare both of them, so if I try to compare both of them, so basically here you have see dx dash fx dash, you have fy and dy, right? You have fy and dy. So basically when I say that okay, so when I say that I have to compare both of them, so if I compare both of them, what I'll get, instead of just y, if I just write Dirac of x minus x dash, then this Dirac of x minus x dash is simply minus infinity to plus infinity e to the power iota x minus x dash times y dy. So if you compare, you will get this. Okay, so one has to remember the definition at the end of the day, that this is on comparison. Let's see, and 1 upon root 2 pi, where I have missed 1 upon 2 pi. See, till now everybody has got everything. I think till now you can see that this f of x is simply, what is f of x? F of x is 1 upon root pi integration from minus infinity to plus infinity gy e to the power iota xy dy. And what is gy? Gy is 1 upon root 2 pi minus infinity to plus infinity f of x e to the power minus iota xy dx. If you straightway put it inside, then what will happen? This e to the power minus iota xy and this plus iota xy, you cannot identify what is happening, because this will then turn into. So always remember, whenever you are doing this kind of double sums, in order to distinguish between the original integral and the integral which has been substituted, we actually we actually use different variables. So basically what I have done, I have changed the variable here, that is instead of x I have written x dash. So this is one thing that you should remember. So what I have done, instead of x I have written x dash. So what is f of x? F of x is 1 upon 2 pi e की power iota xy integration from minus infinity to plus infinity fx dash e की power minus iota x dash y dx dash, and then you have this dy. And don't forget that this e की power iota xy was also there. So I have written e की power iota xy here also. So what will happen? Eventually I will just put the respective variable with the respective function with the respective variables. So for example, fx dash dx dash. This is one of the integration which is running from minus infinity to infinity. Another integration is running over y. So what I have done, I have simply written it as dx dash fx dash minus infinity to infinity e की power iota x minus x dash y dy. Now, if you compare both of them, the term which is associated with this dy, this particular term, I can write this particular term as the Dirac delta function. So basically what is happening, this is Dirac delta function, that is Dirac of x minus y, or instead of x minus y here, since I have changed a variable, so I will write Dirac of x minus x dash is nothing but it is equals to 1 upon 2 pi minus infinity to plus infinity e की power iota x minus x dash y dy. I hope it is clear. So you have to compare both of these equations. See, f of x can also be written in this manner now. F of x can also be written in this manner. So if f of x can be written in this manner, what does it mean? It means that this must be some Dirac delta function, because if it is Dirac delta function, let's say if I say that, let's say this is, just give me a minute so that I can explain you what I want to convey, because I think people are not able to get it what I want to say. Just let me give. Okay, just give me a minute so that I'll be able to explain you. Let's say now I'll explain you backwards. So basically, let us consider that this is this particular thing. Let's say this particular thing, I'm writing it as Dirac of x minus x dash, or whether you write it as x dash minus x, it is one and the same thing. Remember that Dirac delta function is a symmetric function. So if I write it in this fashion, what will happen? Just see. So what will happen? Just understand, this particular thing will become what? This particular thing will become 1 f of x, and this 1 upon 2 pi if you submerge inside. So basically again I'm writing 1 upon 2 pi minus infinite to plus infinite dx dash fx dash, and the remaining term I'm writing in green or some other pen so that you are able to understand what I want to convey. This is e की power iota x minus x dash y dy. Okay, so let's say this particular term which I'm writing in green, if I write it as Dirac of x minus x dash, or you can say Dirac of x dash minus x, because I've told you that Dirac delta function is symmetric. For more details, you can see my lectures on Dirac delta function. Just see, if I write this inclusion of 1 upon 2 pi also, including 1 upon 2 pi. So I'll write including 1 upon 2 pi. If I write entire of this, whatever I've written in green bracket as Dirac of x minus x dash, what I'm getting minus infinity to plus infinity dx dash fx dash, and simply this is Dirac of x dash minus x. So by filtering property, you know that this will be equals to what? F of x. So basically what has become, what I can write this green function indeed as Dirac of x minus x dash. So please understand this particular thing, or if you are not able to follow, please take pen and paper and repeat whatever steps I've done. The end result you should remember that in any case, Dirac of x minus x naught you say, or Dirac of x minus x dash is simply minus infinite to plus infinite. You can write it in 1 upon 2 pi in front, and then I'll write e की power iota x minus of x dash, and then y, and then dy. Remember, this is referred to as the integral representation of the Dirac delta function. This is referred to as the integral representation of the Dirac delta function. This is referred to as the integral representation of the This is referred to as the integral representation of the Dirac delta function. This is point number 1. Okay, so it is quite useful when it comes to quantum mechanics, and we'll see all these things in greater detail as we go along. But overall, understand this is one. And if I want to write Dirac of x, it will be simply 1 upon 2 pi from minus infinite to plus infinite e की power iota x by d pi. Or in terms of the formal language of Fourier transform, what I will do, I will write Dirac x minus x dash as simply minus infinite to plus infinite e की power iota 1 upon 2 pi would follow. Obviously, this is iota k x minus of x dash, and here you will have dk. Just don't forget, if here is x minus x dash, then this particular integral would run. This particular integral will go from this particular integral would be defined, or the variable of integration would be dk, and Dirac of x would then be equals to 1 upon 2 pi, and then I will write minus infinite to plus infinite e की power iota kx dk. Please do remember these two results. Even if you're not able to follow the derivation that I made, please remember these two integral representations. These are quite important when it comes to your exam or otherwise in general also. Okay, what to do about Fourier transform in 3 variables? So for example, if I have to extend my definition, to 3 variables. So for example, then f tilde k or g vector g k, I can write it as 1 upon 2 pi raised to power 3 by 2 minus infinite to plus infinite f of r vector, and then I can write it as e की power iota k vector dot r vector, and then I will write it as d3 r vector. So this is how we extend the definition in the 3 dimensions. And if I want to write the inverse Fourier transform for the above, I'll write f k vector is simply 1 upon 2 pi raised to power 3 by 2 minus infinite to plus infinite f tilde k, and then I'll write e की power minus iota k dot r vector d3 k. Don't get confused with this, but itna remember ko, if this is positive then this will be negative, if this is positive then this will be negative. So both are Fourier transform of each other, so I'll write they represents a pair of 3-dimensional Fourier transform. They represent the pair of 3-dimensional Fourier transform. I hope it is clear. Now you see, we have till now written today we have started with this thing only. So today we have started with the integral representation of Dirac delta function. Now let us move ahead and see a few more things. So this is very important. Another thing that we have seen till now is that in quantum mechanics, if I have to relate my wave function in the coordinate space with the momentum space, this is done via Fourier transform. Okay, so now let us move further. Okay, so let us move further. Now you see, what would be the Fourier transform of the Dirac delta function? Fourier transform of Dirac delta function. So if I want to find the Fourier transform of Dirac delta function, what it will be? It will be equal to 1 upon root over 2 pi minus infinite to plus infinite. I should write Dirac of x instead of f of x. I will write e की power minus iota k of x d of x, and this will be simply e की power iota 0. 1 upon root 2 pi would be there, so I'll get 1 upon root 2 pi simply. So this is how you write the Fourier transform of Dirac delta function, that is Dirac of x. So Fourier transform of Dirac of x is simply constant. Now question arises, what would be the Fourier transform of a constant function? What would be the Fourier transform of a constant function? We did a sort of restriction to a constant function initially. That is, we actually did a single square impulse, not impulse as such, but we did a single square pulse in the first lecture. Now we are doing the Fourier transform of a constant function throughout, not only in the interval, but now I'm saying what would the Fourier transform of a constant function? What would be the Fourier transform of a constant function? So what would be a Fourier transform of a constant function? So let us write f of x is some k, not k, I'll select some other function because k, but then you'll get confused. So see, now if I want to write the Fourier transform, then it is equals to what? It is equals to minus infinite to plus infinite. It will be c times e की power iota minus iota kx dx. This is how you write the Fourier transform. So Fourier transform is given by c e की power minus iota kx dx. Okay, so how would I write? This will be, and 1 upon root 2 pi would also follow, so 1 upon root 2 pi would follow. So Fourier transform would be 1 upon root 2 pi, and there would be a c as well, and then you have this minus infinite to plus infinite e की power minus iota kx. What is this? Just remember, a few minutes before we have written it in form of the Dirac delta function. So this is Dirac of minus x. Whether you write Dirac of minus x or you write Dirac of x, they are one and the same thing. So basically, the Fourier transform of a constant function c, that is f of x is equal to c, I can write it as 1 upon root 2 pi c, and c, well, not Dirac of x, ये हो जाएगा minus k and plus k, because see here the integration is over x, so whatever integration is with, you have to see the argument for that. So I'll get Dirac of k. So this is how I can define the Fourier transform of a constant function. Okay, I forgot one thing. I will have to write 1 upon 2 pi as well. So this will be, I think, 2 pi. Sorry. This will be 2 pi into this. And not c will not come below, c will come here. So I'll get root over 2 pi c and Dirac of k. So one has to remember this particular thing. So the Fourier transform of a constant function is expressed in terms of the Dirac delta function. If anybody has got any problem, kindly let me know in the comments so that accordingly I'll proceed. Okay, so I hope it is clear. Now I will move forward and see one more thing. Just give me a minute before I write that up. So let us do some of the properties at first. And then we'll move further. Okay, now you see, so now let us say that f tilde k is the Fourier transform of is the Fourier transform of f of x. Then what is the Fourier transform of f of x into e की power iota k, and let's say another variable, if I take, let's say x dash, or let us say some different variable, let's say I'll take k naught here. Okay, iota k naught x. So basically what is happening, if I multiply it with something like e की power iota k naught x, because here it is k now, so what will be the Fourier transform of f of x into e की power iota k naught x? This is what is what we want to find. Okay, now you see the f tilde k, I can write it as 1 upon root over 2 pi from minus infinite to plus infinite, and here I've written f of x e की power minus iota k x dx, and instead of this, if I write f uh, like let us say that the Fourier transform of this is, let's say, gk, and this is 1 upon root over 2 pi from minus infinite to plus infinite, and instead of this I'm writing f of x e की power iota minus iota k naught x into e की power of I should have written minus here. So if I want to find the Fourier transform of e की power minus iota k x naught into f of x, if I want to find the Fourier transform of e की power minus iota k x naught into f of x, then how will things behave? So this is like original, there was k here, and this is x. Okay, now you see what will be the Fourier transform. So for Fourier transform gk would be equal to 1 upon root over 2 pi from minus infinite to plus infinite. This is simply equals to f of x into e की power minus iota. This will be k plus k naught x dx. Okay, so you see when you had this kind of things, when you had this k only here, so it was f tilde k. Now instead of k you have this k plus k naught. K plus k naught. So the new Fourier transform, which I have written gk, is nothing but it is equals to the Fourier transform k plus k naught. So this will be Fourier transform of k plus k naught. Okay, so this is how you do things. This is how you do things in the language of Fourier transform. Mostly one has to remember that see, at times you may be confused. For example, some books may say that this is not the Fourier transform. The Fourier transform is with the positive sign. Okay, this may so happen. This may so happen. Don't worry about it. Why don't worry about it? Because after all, these are like Fourier transform. If you say, or inverse Fourier transform, you say both are basically Fourier transforms only. So it may so happen that in your book, or probably wherever you are studying from and wherever I am writing it from, there may be some sort of differences here. So don't worry about those differences, because eventually in exam you're going to find that the definition to you would be supplied for the Fourier transform. So don't worry about it. Okay, so don't worry about it. Now let us move further and see a few more things. Okay. Now let's say, if I say what would be the Fourier transform of let us say that Fourier transform of f of x is simply f tilde. Okay, f tilde k. Now I want to find the Fourier transform of f of x plus x naught. I want to find the Fourier transform of x plus x naught, what it would be. Okay, so Fourier transform of x plus x naught will be minus 1 upon minus infinity infinity. This will be 1 upon root over 2 pi, and this is f of x plus x naught e की power minus iota kx dx. What was f tilde k? F tilde k was minus infinite to plus infinite, and this is f of x e to the power minus iota kx dx. Okay, this is your f tilde k. Uh, if I want to write what would be the Fourier transform of f of x plus x naught, here I can write that my x plus x naught, let's say it is simply equals to y. So x would be simply equals to y minus of x naught. So instead, if I write dx, it will be equals to dy. So this is 1 upon root 2 pi from minus infinite to plus infinite. This I will write f of y e to the power minus iota k. Instead of x naught, I can write what? I can write y minus of x. Sorry, instead of x, I can write y minus of x naught. So I can write y minus x naught. And instead of dx, I will write dy. So what will happen? This particular integration will become 1 upon root over 2 pi. And then this, I can say that this is iota kx naught. Integration from minus infinite to plus infinite f of y. And then you have e to the power minus iota, I think k, y, and the dy. What is this? This is nothing but the Fourier transform of f of x, or you can say f of y. So simply this is f tilde k, which was originally supplied to you, and here you have 1 upon root over 2 pi e to the power iota kx naught. So e to the power iota kx naught into f tilde k. This is how you write your. This is how is your Fourier transform. Okay, so this is your Fourier transform. Okay. Whose Fourier transform it is? It is the Fourier transform of f of x plus x naught. So one has to remember. So overall in exam, one has to remember that this is nothing but these are all the things. These are all those things that you can do in your examination. When you find, well, you can do all these things in examination. These are basic integration things only. But if you're well prepared, so you'll be able to do it in a quicker manner. Okay. Now, let us find the Fourier transform of sines and cosine. So let us find the Fourier transform of sines and cosines. So let us say I am trying to find the Fourier transform of sine of x. So what would be Fourier transform of sine of x? So if I want to write the Fourier transform of sine of x, so what would be easier thing for me to do? It will be easier for me to convert sine in terms of complex exponential. So what I'll do, I'll write this as Fourier transform of 1 upon 2 iota e to the power of iota x minus e to the power of minus iota x. This is all. So basically what will happen, this will be 1 upon 2 root over 2 pi iota, and this is Fourier transform of e to the power iota x minus Fourier transform of e to the power minus iota x. Okay, so okay, so Fourier transform of e to the power iota x into e to the power minus iota x. So just let me show you here what it would be equals to. It would be equals to minus infinity to plus infinity. 1 upon root 2 pi, I will write here 1 upon root 2 pi, and this will be equals to what? It will be equals to e to the power of, this is iota x, don't worry. Okay, so this will be iota kx, and this will be e to the power iota x dx, and this will be equals to what? This will be equals to 1 upon root over 2 pi minus infinity to plus infinity, and this will be equals to e to the power iota k plus 1 x into dx. Now if you remember the Dirac delta function, the representation to the Dirac delta function, if you remember this thing times 2 pi. So if I multiply by 2 pi here, 1 upon 2 pi here, and if I multiply 2 pi here, so this will be root over 2 pi. And what it would be equals what? It would be equals to Dirac of k plus 1. This will be a Dirac of k plus 1. Similarly, this is Dirac of k plus 1. This will be Dirac of k minus 1. So I will get 1 upon, I think it should be 1 upon 2 iota only, because see, root 2 pi and root 2 pi would get cancelled. This will be Dirac of k plus 1 minus Dirac of k minus 1. So this is how you can write the Fourier transform of your sine function. So Fourier transform of your sine function is simply 1 upon 2 iota Dirac of k plus 1 minus Dirac of k minus 1. Similarly, if somebody says what would be the Fourier transform of cosine function. So if someone says what is the Fourier transform of cosine function. So for cosine function it would be 1 upon 2 Dirac of k plus 1 minus Dirac of k minus 1. Plus Dirac of k plus. If someone asks what would be the Fourier transform of sine ax. So now instead of e to power iota x, I'll try e to power iota. Like when I'm writing in terms of complex exponentials, then sine ax can be written as e to the power of iota ax minus e to the power minus iota ax divided by 2 iota. This is how I'm going to write it. So how would I write Fourier transform of sine ax? So Fourier transform of sine ax would be then equals to 1 upon 2 iota Dirac of k plus a minus Dirac of k minus of a. So this is how you can write my Fourier transform of sine of ax. Now, one of the important things that usually you will see that in examination, or it will also come. What is the Fourier transform of Fourier transform of you can say e to the power minus of ax, or e to the power minus x. Let us take it minus modulus of x. Let us take it first. That is, we want to find the Fourier transform of e to the power minus of modulus of x. What do you think that What do you think that this particular Fourier transform would be like? Okay. So the Fourier transform e to the power minus of modulus of x, what it would be like. So I'll write f tilde k is simply 1 upon root over 2 pi from minus infinity to plus infinity. Here I will write f of x. Instead of f of x, I'll write e to the power minus modulus of x e to the power iota kx dx. Okay. Now you see this is modulus. I know how to define modulus. Modulus of x can be defined as simply x if x is greater than 0, and it can be defined as minus of x if x is less than 0. Okay, so how would my f tilde k behave? My f tilde k would behave as 1 upon root over 2 pi, and this is from minus infinity to 0. You can write it as e to the power of x simply, so it is e to the power iota k plus 1 x dx, and from 0 to infinity it will be simply e to the power like this minus. Okay, now you see if I want to write this up, what would I get? I would get f tilde k is simply 1 upon root over 2 pi, and you see this theoretical integration, you will get 1 upon iota k plus 1. Okay, and this integration you will get minus 1 upon iota k minus 1. Now you will be thinking, what about infinity? See, for example, if I place infinity, what would happen? See, I'm just showing it here. See, e to the power iota k plus 1 x, and you have this limit x tends to minus infinity. That is the lower limit I'm thinking of. So if I'm thinking of lower limit, it will be e to the power iota kx. See, this is a bounded function. It will always remain between it will always, like for example, if you take the modulus of it, the modulus of it would be 1. And in other words, you can write it in the linear combination of sines and cosines. So basically, you can write it as sine kx and cos kx or something of this sort. Okay, so basically what happens is this is a bounded function, so it will remain between some two values, like two values. For example, if I say, what do you think your a cos theta and b cos theta, the range of a cos theta and b cos theta, you know, it is always between root over minus root over a square plus b square to root over a square plus b square. But if I'm saying e ki power iota kx, then I can write e ki power iota kx is simply cos kx plus iota sin kx. So here also, you know, it will lie between minus root 2 plus root 2. In any case, this is a bounded function, but then there's another function which is e ki power x, and now x tends to minus infinity, this will go towards 0. So any bounded function when multiplied with 0 will eventually give you 0 only. So forget about the lower limit, forget about the upper limit here, it will also go towards 0 only. So therefore I've written this, and effectively I found that my f tilde k would be equals to 1 upon root 2 pi, and there you have this, on the lower side you have this minus of k square minus of 1, and the upper side you can see this is equals to minus of 2. So eventually you will get this, eventually I'll get 1 upon root over 2 pi 2 upon k square plus 1. Okay, and so eventually always remember that if I have to write the Fourier transform of e ki power minus of modulus of x, it will be equals to 1 upon root over 2 pi 2 upon k square plus 1. And if I want to write the inverse Fourier transform of some k square plus 1, it would be something proportional to e ki power minus mod x. I'm not saying what would be the what would be the constant values. There would be some constant values, so remember this. Now, why I'm laying stress on this, I will let you know tomorrow, because in one of the CSIR net examination, this particular question appeared, and obviously this is a quite standard thing to see, you can see in your exam, but at times students are not that aware. So they chose to do this thing using contour integration, and they did not get a modulus, and their answer was wrong. So I will let you know what is the mistake that is going on in that particular scenario. But right now, just remember, if I am writing the Fourier transform of e ki power minus modulus of x, it will e ki power minus modulus of x, it is 2 upon root 2 over 2 pi. This you can like at times you'll find that in questions it may not be given to you in exam. It is entirely the choice of the examiner to give it or not give it. But overall, remember 2 upon k square plus 1. This is a kind of this is something that you can think of. This is the Fourier transform of 1 upon k square plus 1 is a Fourier transform of e ki power minus mod x. This is one thing that you should remember. Okay, so let us take that question itself. Let us take that question itself, and then let us understand what was the problem. So this question appeared in the net exam of, I think, 2016 somewhere. Yeah. So I'll show you that question. That was December 2016, and people chose to do it using complex integration. So what was the problem? Let me know. Let me show you. So minus infinity to infinity, this was dx, and here it was given f of x e ki power iota kx. So now you see, in the entire discussion I have taken a negative, but in examination they gave this as the Fourier transform of f of x. So this is how they defined it, their Fourier transform. So they defined Fourier transform of f of x in this manner, and they were asking what is the Fourier transform of what is the Fourier transform of f of x given as 1 upon x square plus 2. So from above discussion, from the above discussion, it is quite clear that the Fourier transform of this particular function would be what? It will be proportional to e की power minus of uh, modulus of x. Na? So here you have this, I can write it as 1 upon x square plus root 2 whole square. So I can write it as minus 1 upon root over 2. Okay, so one can see that this is proportional to sort of this, because here it was 1. So okay, so here it will be. So for this I will again give you another property so that you'll be able to judge what I want to say. Just give me a minute. I will give you that property also. So I will first write the scaling property. Okay, so I will first write the scaling property. So I will write the scaling property at first so that you will be able to get it. So this was the question in the exam. Now let me show you what is the discrepancy. So let us use the scaling property. Now what is scaling property? Just let me give you. So for example, if the Fourier transform of your function f of x is simply f tilde k, then what would be the Fourier transform of f of ax? So it will be simply equal to 1 upon a f tilde k upon a. How come? Just let me show you. So Fourier transform of f of x is minus infinity to infinity. Let's say I use this definition. Let's say I use the definition given above. So it is equal to, and remember what is the Fourier transform of, I'm writing it here, what is the Fourier transform of e की power minus modulus of x? It is 1 upon simply k square plus 1. Some root 2 pi is following, 1 upon root 2 pi is following, but just forget about it, because see here you know the definition does not contain 7 upon root 2 pi. So even if you want to write it, you can do it, or if you don't want to write it, it's absolutely fine. Okay, so this you don't have to forget that this was the case that we did initially, and if you want to drop 1 upon root 2 pi, that is absolutely up to you. Okay, now if I want to write what is the Fourier transform of f of x, it would be f tilde k would be equals to minus infinity to infinity, and it will be e की power iota kx. I'm using the definition that has been given to me, f of x dx. Now instead, if I want to find the Fourier transform of f of ax, so what would be the difference? So instead, if I am supposed to find what is the Fourier transform of f of ax, so what it will be? And let us say a is positive. Let us say a is positive. Let us say a is positive. So it will be minus infinity to plus infinity e की power of iota k, and here you have ax, and here you have f of ax, and if a no, sorry, this will be x only, and instead of x I will write ax, and this is dx. Now if I write ax as simply y, so your dx will simply become 1 upon a dy. So if I use this here, what it will be, minus infinity to plus infinity e की power iota k, I will write y upon a instead of x, and here I will write f of y, and here I will write 1 upon a dy. So it is simply equals to 1 upon a minus infinity to infinity e की power of iota k upon a times y, and this is fy dy. You see, this particular integration is what? This particular integration, when I had done over e की power iota k y, then it was fk. Now f tilde k. Now it is f of k by, so I'll write 1 upon a, and this is f tilde k. So this is the scaling property. This is one thing that I forgot to tell you. This is referred to as scaling property. If there is a negative minus 1, then you will find that these limits of integration would change. So eventually I will write it as, so if f of x, this the Fourier transform of f of x is simply f tilde k, and if I'm asking what will be the Fourier transform of f of ax, irrespective whether a is positive or negative, then I can write it as 1 upon modulus of a f tilde k. f tilde k upon a. This is how you can write it up. Okay, this is how you can write it up. Okay, now you see the question that was given to you was this. So for example, uh, I want to find the Fourier transform of f of x, where f of x is simply 1 upon x square plus 2. Okay, it is x square plus 2. So let us derive a simple result to it, and then we'll see. So we know that Fourier transform of e की power minus of modulus of x was, I think, if you use this 1 upon root 2 pi, it's fine. If you don't use it, then it is 2 upon k square plus 1. This is how I think the answer was. If you remember, let me show you. Chalo, let me use, just let me show you. Here it was. So if you want to use 1 upon root 2 pi, it's up to you. If you don't want to use, then it is 2 upon k square plus 1, because the definition says me so, so therefore I'm not using it. So I'm just using 2 upon k square plus 1. Now instead of this, if I'm demanding, let's say, Fourier transform of e की power of minus of a mod x, then it will be equals to what? It will be equals to 1 upon a Fourier transform of, this will be Fourier transform of, instead of k I will write k upon a. So instead of this I will write 1 upon a, and then I will write Fourier transform of, like this will be 2 upon k square by a square plus 1, and this a square will go above. This will be 2a upon simply k square plus a square. Okay, so this is one thing. Now instead of this, so I know that now the Fourier transform that was given to me was this. So I have to find the Fourier transform of this particular function. So e की power minus modulus of it. Yeah, sorry. If I write that inverse Fourier transform, again inverse Fourier transform is also Fourier transform. Don't worry about it. So inverse Fourier transform of 2a upon k square plus a square will be what? It will be equals to e की power minus of a times modulus of x. So in any case, one thing is quite sure, that if I am trying to find Fourier inverse of 1 upon x square plus 2, it will be proportional to e की power minus of root over 2 modulus of, here it will be k, I think, because here if it is x, then it will be k. So one thing is very much clear, that this is something that option should reflect. And in examination, if you see this question, when it was asked, option had contained without modulus options also, like the option contained options that were given to you in the examination. Let me give you those options also, so that you'll be able to understand what I'm trying to make. So the options that were given to you were these. So one thing is very much clear, that modulus should appear. Now what was the question given to you in the examination? So the question that was asked in examination was about this. So question that was asked in examination was this. So one wanted to find, one had given you that this thing is your Fourier transform, and the examiner wanted from you that you should find the Fourier transform of 1 upon x square plus 2. It was asked to you that find the Fourier transform of 1 upon x square plus 2. And the options that were given to you, option number 1, it was given root over 2 pi, e की power minus root over. Option number B, it was root over 2 pi, and then it was e की power minus root over 2 ck. That is what I was saying, that there was an option without modulus. So therefore one thing is clear, that this cannot be an answer. But see what discrepancy students face, that I want to suggest. At this particular thing, you cannot work with the proportionality. We'll have to somehow find the integration as well, because you see here some constants are given to you. So we'll have to solve it. I'll solve it for you, don't worry. Okay. So this was what was given in the examination. Okay. Now you see, in order to solve this particular integration, one has to see that here I have taken the help of inverse Fourier transform. Okay, inverse Fourier transform. I've come to the conclusion that what will be the proportionality? Proportionality would be e की power minus root 2 modulus of k. So these two things would get cancelled. Now I have to find these two things. So I will have to somehow find the integration. I will have to find the integration. I cannot escape that. And this is what students did. And now let me show you what was the problem. I would not say discrepancy, but what was the error that students did. So for example, when they started evaluating this was this, and 1 upon x square plus 2, and then they wrote e की power iota kx dx. Now, all of those who have taken the classes on complex variables that I have taught you, and if you have not taken it, then let me introduce to you something called as Jordan lemma. What does this Jordan lemma say? It says that whenever you have to integrate such integration which I have shown you, you can replace this integration by a complex integral. You can replace the given integral in front of you by the help of a complex integral over the upper half of the semicircle. Okay. Just let me write you the proper statement so that you will get what I want to suggest. Okay, so that actually was a problem, and eventually people got wrong answers to it, and I want to explain you what you have to pay attention to. So just give me a minute, I'll show you. So for example, so whenever you have these kinds of integral, that is the integral which contains e की power iota, and you have a function multiplied with it. So for example, whenever you have this kind of thing, so you can replace this by integration over a semicircle contour given by gamma e की power iota kz, and you have this fz dz. I should write gz because fz is this already. So if you can replace this integration by this, and what is gamma? Gamma is the upper half of the semicircle. Gamma, you usually take it as the upper half of the semicircle from minus r to plus r. And let us say this is CR. CR is the semicircular, this particular, only this upper half. Okay, only this upper half is there. And if you want to evaluate this integration, what happens is here k is greater than 0. One thing you should remember, here k is greater than 0. And what happens is that when you evaluate this integration over the upper half, the integration over the CR, that is integration over the CR, this e की power iota kz f gz dz goes to 0. How does that go? Let me show you. Here what is gz? Gz is simply 1 upon z square plus 2. Just compare it. Okay. And what is any complex number on the CR would be z is equal to r e की power iota theta, where theta varies from 0 to pi. So if theta varies from 0 to pi, this will constitute your upper half of the semicircle. Okay. So if I integrate this up, this will be less than equal to integration over gamma, and this will be e की power iota kz. This will be 1 upon z square plus 2 ka mod, and then you have a dz mod. And you know that this particular integration will be less than equal to this is 1. See, 1 upon z square plus 2 ka mod. So I'll write z square plus 2 ka mod will be always greater than equal to modulus of z ka whole square minus 2. If I divide them, it will be less than equal to 1 upon modulus of z ka whole square minus 2. And what is modulus of z? Modulus of z is simply r. So I will write 1 upon z square plus 2 would be less than equal to 1 upon r square minus 2. So if I write this as 1, I'll get 1 upon r square minus 2. And what is dz ka mod? Dz ka mod is all these elemental lengths being added. So what these elemental lengths being added on the upper half of the semicircle would give you? It will give you simply pi over r. And as r tends to infinity, this will go towards 0. So what happens is, if I want to find an indefinite integral from minus infinity to plus infinity, which is like e ki power iota kx, and you have, let's say, g of x. Here g of x is 1 upon x square plus 2. Then you can write it, instead you can write it in this terms, e ki power iota kz gz f gz dz. And you know what is this integration? This integration is 2 pi iota into the sum of residues on the upper half of the plane. On the upper half of the plane. Now what happens is, I have already told you that this integration can be divided into two parts. One would be CR. This particular thing will go to 0. That is on this particular semicircular sort of curve. This particular integration would go to 0. And the integration over from minus r to plus r will become an integration from minus infinity to plus infinity, e ki power iota kz e ki gz dz. And you know, on the real axis, whether you write z or whether you write x, they are one and the same thing. So basically these two integrals become equivalent. These two integrations become equivalent as r tends to infinity. One has to remember that this particular integration can be replaced by this complex integration, and this complex integration is equal to 2 pi iota sum of residues on the upper half of the plane. Okay, and when students evaluated using this, so now let us come to the main problem. So what students did, students tried to do this particular thing using this. So basically how to find this Fourier transform? So basically Fourier transform of 1 upon x square plus 2 would be equals to integration from minus infinity to plus infinity e ki power iota kx and 1 upon x square plus 2 dx. Now this the students wrote it as integration over gamma, where gamma is the upper half of the semicircle. I'll write upper half of the semicircle e ki power iota kz 1 upon z square plus 2, and then you have this dz. And you see this particular function has two poles. This is an entire function, forget about it. This particular function has two sort of, you can say, singularities, and these singularities are basically poles only. They are simple poles. So one has to find the sum of residues. So 2 pi iota into sum of residues. So where you have to find residue, you have to find residue at z tends to root 2 iota. So z minus root 2 iota into e ki power iota kz into 1 upon z minus root 2 iota into z plus root 2 iota. This is how you do. This is how you find the residue for simple poles. This you cancel out, and eventually you got 2 pi iota into e ki power iota. If you take root 2 iota here, so if I take root 2 iota here, so what I'll get? I'll get simply minus of root 2 k, and here I'll get 1 upon 2 root 2, I think iota. Iota gets cancelled, 2 gets cancelled, so eventually you end up getting pi upon root 2 e ki power minus root 2 k. Now here you see the options were given to you. Like one of the options suggested pi upon root 2 e ki power minus root 2 k, and most of the students tick this option as correct. However, one has to understand from the theory that we developed for e ki power minus modulus of x, so one can clearly see that if I have to find this particular Fourier transform of 1 upon x square plus 2, it should contain modulus of k. Now you would be thinking, what is the mistake in this particular entire scenario? The first mistake that you should understand is this particular Jordan lemma. In this Jordan lemma, we take this upper half of the semicircle provided k is greater than 0. Provided k is greater than 0. But while we are evaluating Fourier transform, we have not put any such constraint on k. So basically, this integration is correct. This integration is correct provided k is greater than 0. This integration is correct provided k is greater than 0. Now what if I'll write what if k is less than 0. What if k is less than 0? Then the Jordan lemma suggests that the integration that you're doing on the upper half, you have to do on the lower half. Then construct a semicircle on the lower half. Semicircular contour on the lower half. Okay, now we have to construct. So basically, this is true for all k greater than 0. Now I'm considering the case k less than 0, because you see, understand the derivation that we did for the Jordan lemma, we did for all k greater than 0. Point number 1. So for all k greater than 0, we can make particular this thing on the upper half of the semicircle. Now, if I make on the lower half of the semicircle, what first thing that you have to see is that you're. Now let me just show you. If I construct a semicircle contour on the lower half, so this is how it is. And remember, your k is less than 0. Remember, your k is less than 0. So for the case of k less than 0, one is clear. Now the singularity that will be inside is minus root upon 2 iota, and don't forget that this integration is going in this direction. So basically it is going in the clockwise direction. So basically what will happen, why? Because this k is less than 0. So for example, if I have to take it from minus infinity to infinity, if k is less than 0, then it will go from infinity to minus infinity. So just to balance it, I have to take a contour which is oriented clockwise. So if I am writing this f of x e ki power iota kx dx, I can write it as the contour integral gamma f of z e ki power iota kz. Don't forget that k is less than 0, dz, and this is oriented clockwise, not anti-clockwise, but clockwise, not anti-clockwise but clockwise. And you know that whenever you have to write it, this integration, if the orientation is clockwise, then you have to take a negative also. So negative 2 pi iota into sum of residues, which is limit z tends to minus 2 iota, minus of 2 iota. Here you will get e ki power iota kz. Don't forget that your k is negative, so you have to keep that in mind. Okay, you have to keep that in mind. 1 upon z square plus 2, I'll write z minus root 2 iota into z plus root 2 iota will get cancelled, because you have to write z plus root 2 iota in order to evaluate the residue. So this gets cancelled. There is a negative, and then there is a negative also. So what I'll get, I will simply get it as, if I write minus root 2 iota here, so this will be minus 2 pi iota divided by minus 2 root 2 iota, and here I'll get e ki power minus this root 2 iota. So I'll get simply iota ka square is 1, so I'll get k times root 2. You see, there is an iota here. If I write iota minus root 2 iota, iota square is minus 1, and minus would get absorbed. So basically you will get pi upon root 2 e ki power root 2 k when k is less than 0. So if I have to summarize both of the results, what I'm getting that integration is simply equals to pi upon root 2 e ki power minus of root 2k for all k greater than 0, and it is equal to e ki power root 2k when k is less than 0. If I have to summarize the result, I will write pi upon root 2 e ki power minus of root 2 modulus of k. So this is how you write the result. So therefore, the option that suggests you this is the option number C. So the correct answer to this option, the question was, I think, sorry, D, not C, D. So pi upon root 2 e ki power minus root 2 modulus of k. So this is what I have for today. I'll again take a class on complex this thing Fourier transform tomorrow, and probably a day after, and then things will finish off. Please keep revising whatever we have done, and please remember this is an important topic for your exam. Okay, so I'll hope to meet you tomorrow. Till then, take care.